Hi, today we'll be going over the project of assessing player contributions in a game of soccer with the use of Shapley values. Now let's take a look at what Shapley values actually are. So the idea of Shapley values originated from D-player cooperative games with fair credit allocation. um, where each player would be given a utility score based on a utility scoring function for every subset or collision of players. And these scores will essentially accumulate towards the payout of that player for that particular collision. This idea can be ported over to a D-feature machine learning problem where, let's say, we have n observations and D features, and Shapley values can then be used to explain a local prediction, as in one particular prediction, as to how each of the D features contributed towards having that prediction as opposed to the average prediction made by the model. So, like we've seen before, the utility function essentially relies on or is subject to four key axioms, and these properties must be satisfied. So these are efficiency, null pair property, symmetry, and additivity. So the Shapley value of a feature can be defined as the weighted average of the marginal contributions of that feature, right? So the idea is, let's say we have three features. One collision would be no features, another could be any two of them, the other could be just one, and essentially each collision is the permutations of all feature combinations. And for each collision, the model prediction with a particular feature and the model prediction without a particular feature is obtained. And once these two values are essentially, if we take the difference, that's the marginal contribution of that particular feature for that particular collision. And if that marginal contribution is averaged over all collisions for the same feature, we essentially get the Shapley value of that feature. Now this can be computationally quite expensive, right? And that's handled by Shapley additive explanations, in other words known as SHAP, which was developed by Lundberg and Lee back in 2017. What SHAP does is it transforms the collision space into binary and then um, solves a linear problem, a linear model, where the weights of the model are interpreted as the Shapley values. Now, when we say SHAP, we are essentially talking about kernel SHAP, which is a model agnostic approach of calculating SHAP. There's linear SHAP, which is a model specific approach to get Shapley values for linear models. Then there's tree SHAP, which is a model specific approach used for decision trees, random forests, boosted trees, bagged trees. And similarly, we have deep SHAP, which is specifically catered for neural network architectures. Other more advanced approaches include RKHS SHAP, which is a model-specific approach to get Shapley values. So it's specific for kernel-based models. Examples include kernel regression, kernel SVM, etc. And then there's PrefShap, which is suited for computing Shapley values when it comes to preferential data, player versus player, or something like that. Now, let's look at the motivation behind this project. So, in every soccer game, it would it not be great if we could assess the contribution of every player towards a particular result? Let's say two different teams are facing. If we had all the players participated in the match, all the players who participate in the match, and if we could understand, okay, by looking at the Shapley values as to how or how much each player contributed towards the home team winning or the away team winning or a draw. So this will allow us to capture the dynamic nature of the game, and then we could look at the contributions and also reflect that with the player statistics. This would help a manager, for instance, choose his best lineup for the next match based on the opposition, based on the players, or based on the nature of how the players generally play. So ideally, by the end of this project, uh, I wanted to assess player contributions for one particular team in the Spanish league, let's say Barcelona. Now let's take a look at how the data was obtained and how the data set was essentially formulated. It was quite difficult to find uh, soccer data, which included team statistics, player statistics, results, and everything together. But fortunately, I came across the SofaScore API, where they had many different REST API endpoints which could be consumed to obtain information like league IDs based on the country, match IDs, results, statistics, player statistics, biography, etc., etc. So for this project, we mostly used match results, match statistics, player statistics, and four different seasons of the Spanish League was considered. So it's 2018, 2019, 2017, 2018, and then 16, 17, 15, 16, essentially. Now, if we look at how the data was formed, so initially the API was consumed, and then match by match team statistics, player statistics were obtained, and then those were parsed to form a tabular data shown here. So let's say we have 11 players, right? So the idea is I also had to take a look at the different formations available, and it was found that the maximum, like if you know anything about soccer, you would know that the formations are something like 4-3-3, 5-3-2, 4-3-2-1. So at best, 5 defenders, at best, 5 midfielders, at best, 3 forwards, and obviously 1 goalkeeper. So the way the dataset was formed was that for a home team, we had home goalkeeper statistic 1, and that statistic can be anything. Let's say number of passes made, number of saves, right? Home goalkeeper stat 1, away goalkeeper stat 1. Similarly, home goalkeeper stat 2, away goalkeeper stat 2, up to n number of stats, right? And then we have the same for defenders, where it would be home defender 1, stat 1, away defender 1, stat 1. Same thing for the next statistic. And this is just for one defender, and we would have 5 defenders for home and away, right? Same way we have for midfielders, and then I've shown what it would look like. A simplified version of it would look like for a forward, right? Now, overall, I found that there were 46 different types of statistics for players. So I made sure each player was subject to those statistics in the dataset. The problem here was the API sometimes did not return the same statistical measures for each player. Like some players had some missing. Some players did not have that information, right? So I essentially have a problem, had a problem where each uh, player was not like the number of features or the number of statistics for each player was not the same. So this essentially could be addressed by an approach called deep sets. So I've incorporated that. Deep sets essentially an approach to facilitate observations with varying number of features. So the first thing I did is for any particular player, if a particular feature is missing, it was replaced with a 0, right? So once the data is converted into sets, each observation, rather than being a set of columns, rather than being a certain number of columns, each observation was a set of player vectors, right? Where the values in each player vector are the statistical measures, right, for different features. So overall, considering we had one goalkeeper, a max of 5 defenders, a maximum of 5 midfielders, a maximum of 3 forwards, we had 28 players overall in the set, right? So, and obviously the labels would remain the same: home win, away win, draw, etc. Now, let's take a look at how we would fit a machine learning model that would take in uh, a set as an input, or where each observation would be a set of player vectors. So 3 different models were considered in the study. Those were random forest, TabNet, which is a neural network-based architecture specifically catered for tabular data, and XGBoost, which is uh, sort of like a modified model of boosted trees. So hyperparameter tuning was done for each of the 3 models, and XGBoost seemed to be the best, and TabNet was kind of the worst. And I guess that's consistent with the idea of neural networks not really performing as well as random forest or boosted trees when it comes to tabular data. So after tuning, the test accuracy for the XGBoost model was about 75.3%. And this can be improved by probably doing some feature engineering or by including some other features. There's one thing I forgot to mention. In the observations, for each observation, we removed any team-based statistics and also any obvious statistic like number of goals, number of assists, own goals, because that would make the outcome pretty obvious, right? So yeah. So now we take a look at how the machine learning model would accept set inputs. So if we look at the idea of deep sets, one of the most important things is the aggregation function, which essentially takes in each observation and sort of maps the items in that set to a different representation, which is permutation invariant. And in this case, we used the summation aggregation function. So let's say we have a total of 28 players in the set, and each player has 46 feature values, right? Now, if we separate the home players and the away players, and we would then aggregate the feature values, right? So column by column, right? So that we would have for every match for a home team, let's say we would have 46 aggregated feature values. For the away team, we would have 46 more. So there's a typo there. So after doing the aggregation, each match should be represented by a row of 92 aggregated feature values, right? The next step was to pre-process the feature set, which is standard scaling. And then the next step was fitting the model and getting the model predictions. So let's take a look at the aggregation function a little bit. So if you look at this one particular observations, so let's say P1, P2, up to P28 are players. We add feature by feature. So F1 for player 1 plus F1 for player 2 plus F1 for player 28. So that's one aggregated feature. And same thing for F46 for player 1 plus F46 for player 2, F46 for player up to player 28, right? And that's for the home team. And then we get the away team players do the same, stack them side by side. So we have a total of 92 aggregated features. So let's get to the business end and take a look at how we can actually use the Shap package to compute Shapley values where the dataset has been formulated as sets. Now by default, initially I wanted to try out kernel Shap, sort of the de facto model agnostic Shap. But kernel Shap does not take in sets of players, right? So this was addressed by the creation of our wrapper model, which uh, underneath would have that optimized XGBoost model. But this wrapper would take in uh, observations where each observation was a set of player vectors, right? And then it would predict the winner. And all the aggregation and the pre-processing was moved within the wrapper. The next thing that was done was associating kernel Shap with the wrapper. So normally for a dataset of size, let's say n observations and k columns or k features, kernel Shap would give k Shapley values for a particular observation. And Shapley values would represent feature contributions, right? But in this project, the goal is to get player contributions, but we've essentially made the dataset in such that each row is a set of players, but each player has its own set of values, right? So the idea would be for a certain test observation, which is a set of players, for every player, right? We calculate the Shapley value for observation with player, also the Shapley value for that observation without the player. And if we deduct or if we take the difference between those, we could get a vector of values that would represent the or some form of contribution of that player, right? And then we save the contribution vector of each player for the observation. So as of right now, there is not much in terms of results. So I've just successfully computed Shapley value vectors for each player for a given match, but I need to find a way to map the vectors to a different representation because these vectors are now like each value in the vector corresponds to one feature value for a player, but we want to get player contributions, so these probably a summation or some sort of mapping to represent the entire thing in terms of a player. um, uh, so it could also come down to looking at custom value functions for the computation of Shapley values. So it depends on the scenario, but let's see where the project goes. So if a kernel SHAP is successful, other approaches based on the data would need to be considered as well. Because the best model here was XGBoost, might need to try tree SHAP as well. So that was that. So thank you. I hope I can do something, can proceed with this project and get some results in due time. So, yep,